So in this video, we're going to look at example 3, which is still in section 8.2. And remember, the big deal about section 8.2 is that your standard deviation is going to be known in these examples. We'll talk in the next example about what to do whenever your standard deviation for the population is unknown. So before we get started on this example, I just wanted to point something out about the previous page. So we've already talked through this procedure, and we talked through a big long example on how to apply this procedure. The thing that I wanted to point out about this page, though, is that in the example that we just talked about, what we ended up doing for the critical value approach was I wanted to know this critical value that had our significance level as its right area. And this had a corresponding critical value that we saw of 1.28. We looked that up in the table. But we often choose as our level of significance something like 10%, 5%, 1%. So we're pretty consistent in the level of significance that we choose. And therefore, they've been nice to us and they've just recorded the critical values that correspond to a measurement of 10% or 5% or whatever. So all of those critical values are over here in this nice table, which can save you some time. You don't necessarily have to look them up in that standard normal distribution table. You have all of the critical values for the things that we're going to be using here. So you can just refer to this little table if you need the critical value like we did before. Okay, so let's look at example 3. Here it says, in 2005, the mean retail price of history books in Lubbock was $78.01. This year's retail prices for 40 randomly selected history books show a sample mean of $81.44. At the 1% significance level, does this data provide sufficient evidence to conclude that this year's mean retail price has increased from the old mean? So notice that this is a few dollars more than the old mean, and we sampled just 40 randomly selected history books. So you can imagine things this way if you'd like. It's pretty unlikely that you would happen to choose, if you're just picking at random, 40 expensive books, right? Instead, because you're choosing so many books, this is a large sample size, you would expect the mean that we get from those 40 to be pretty close to the mean that the actual population has. So what we're trying to do is we're trying to measure the current year's mean retail price, and we're trying to compare it to the old mean retail price of $78.01. And it says, assume that the population standard deviation here is 761. So in this case, our sigma is known, it's 761. So that means we can apply these techniques from section 8.2. And remember, the assumptions that we need in these cases are that we're taking a simple random sample from the set of books. So here we had 40 randomly selected history books. So that would be a simple random sample. And then we also need either the original distribution to be normal or a large sample size. Now, in this case, our sample size is 40, so we do have a large sample size. And then our last assumption is that sigma is known. So therefore, we have all of the assumptions that we need on the previous page. By the way, I think it might be a good idea for you to, while you watch this video, just have this in front of you. So maybe pull up the notes on a separate tab or something and keep this video in one window while you have these notes in front of you so that you can just verify that we're going step by step through this procedure. So notice that what I just verified was the set of assumptions that we have up at the top. We have a simple random sample. We have a large sample that we're taking. Our n is larger than 40. And sigma is known. Okay. So now we're just going to go through all of the steps in the procedure. The null hypothesis is always given by equality. So this would be mu is equal to the old mean, which is 78.01. And the alternative hypothesis that we're supposed to be testing is whether, Sorry about that. The alternative hypothesis that we're supposed to be testing is whether the mean for this year has increased from the old mean. So we'll have that H naught is equal to, or sorry, H naught is mu equals 78.01. And the alternative hypothesis is going to be that mu has increased since the mean from 2005. And we also know the significance level. It was just told to us in the prompt. So it says at the 1% significance level. So alpha would be 0.01. In step 3, we're computing the test score. So we're going to take our sample mean, which was 81.44. We're going to subtract the mean, like the old mean, which is 78.01. This mean that you subtract off here is always the mean that you get from the null hypothesis. So that's where I'm getting this 78.01. So then we divide by this standard deviation for the sample means. So this would be dividing by 761 divided by the square root of 40. Now, if you're doing this in a calculator, I would put the parentheses like I have here, because it's important that you're dividing not just twice in a row, but instead you're dividing by this fraction. And those are different if you just try plugging them into your calculator without parentheses. So I would probably parenthesize like this in my calculator. Parenthesize the full numerator and also parenthesize the full denominator. So what I'd recommend is if you're a little unsure about computing this, I already punched this into a calculator and I got 2.85. I would recommend that you do the same. So you can just check with these numbers that you can plug this into a calculator and get the appropriate expression. So this should come out to 2.85, assuming you plug it in correctly. And that's the test score that we're looking at. So in other words, whenever we standardize, our picture looks something like this. So we've standardized, and our test statistic is way over here. So in other words, we've gotten that the mean from the sample is significantly far to the right relative to the mean that we originally had in 2005. The 2005 mean would get mapped to 0 here, and our sample mean is way over here to the right. But we need to decide whether this is far enough to the right that we are willing to reject the null hypothesis. And to do that, we'll talk about these two approaches again, the critical value approach and the p-value approach. For the critical value approach, we need to decide what the critical value is, and that's the z-score corresponding to our significance level of 0.01. For that, we could use the table, or we can just scroll back up to this page and we look for the appropriate z-score. It lives here. So it looks like the z-score corresponding to a 1% significance level is 2.33. So I would come back down here and I would say that z at 0.01 is equal to 2.33. The test statistic that we got, we just computed to be 2.85. And notice that 2.85 is further away from 0 than 2.33. So in other words, what we just did is we found that our critical value was 2.33 and our test statistic is further to the right. So therefore, our test statistic is more extreme. I'll say than our critical value. And therefore, what we should do is we should reject the null hypothesis. We'll get the same conclusion if we take the p-value approach. Remember that the p-value approach is to compute this area that lives over here to the right of our test statistic. And if that area is smaller than the area that than the error that we're willing to put up with, which is our level of significance, then we would reject the null hypothesis. So first, what we want is we want to look up the area to the right of 2.85. And to do that, what I'll do is I'll pull up the table. We want the area to the right of 2.85, so I would come over here to the 2.8 row and the 0.5 column, and those intersect here. So I get a 0.9978. That means that the area to the left is 0.9978. So let me, sorry about that. So what we just saw is that the area to the left of 2.85 is 0.9978. And that means that the shaded area that we're looking for is 1 minus that, which would be 0.0022. So we would get a p-score of 1 minus 0.9978, which is 0.0022. And here our p-value is less than or equal to alpha. Because remember that alpha was, in this case, 0.01. So because our p-value is smaller than alpha, the instructions say that we should reject the null hypothesis. So these should come to the same conclusion no matter what. These are just two different ways of thinking about it. The left side here is doing this by computing the z-scores and deciding if our z-score from our test statistic is more extreme than it's supposed to be. And the right side is doing the same sort of comparison, but this time with areas. So on the right side, we're computing what the probability would be of getting such an extreme z-score as the one we got. And in both cases, what we're getting is that our test statistic is so far to the right that it's past our critical value, and therefore we would reject the null hypothesis. So if you want to interpret these values, what I would say is that there's only a 0.22% chance that we'd get such an extreme test statistic if H naught were true. So we reject H naught. In other words, if H naught were true, then we know that the distribution that we would be looking at would be something like this top one that I've drawn. But notice that the z-score that we got was far out to the right. It was at a 2.85 rather than something near 0. And because this lives past our critical value, or because it has a p-value that's small enough, in either case, we're going to reject H naught. We suspect that the actual average has increased since 2005. So that's how we complete the problems from section 8.2. Next, we're going to talk about problems in section 8.3. The strategy is going to be exactly the same. It's just that in 8.3, we don't necessarily know the value of sigma, which is the population